Okay. Thank you, everybody, for coming back to our online seminar series. Today, we have the pleasure of having Sebastián Maldonado. He's a full professor at the Universidad de Chile, and this is one of the partners in our NEEDS project. Sebastián is at the business school, so his publications are mainly in business analytics. He counts more than 60 publications. We all know his work, for instance, on feature selection for support vector machines. Sebastián has been in the past the president of the Operations Research Society in Chile, and currently he is the vice president of the IEEE Society on Computational Intelligence. We are extremely happy that he is going to talk today about cost-sensitive classification, but even more important, causal classification. So the floor is yours, and thank you very much again for accepting our invitation.
Thank you, Loli, for your kind introduction, and also it's a great honor to be one of the outliers here as non-European data scientists in this blue dot that represent the University of Chile here in the NEEDS logo. Today is also a special day, and I would like to take the opportunity to acknowledge the amazing work you have done together with Emilio and Belén in the Sevilla group for inspiring female researchers and do this top research that has bring you actually to be the leader of this amazing network. So this is also an inspiration for me because we are in South America and we are so far behind in integrating women into STEM area, mathematics, computer science. So I really would like to take the opportunity to say that on Women's Day. So shame on me. Here is the list of different. This talk encompasses 4 papers. Here's the list of all the co-authors I wanted to acknowledge. Only 1 female author of all these other authors. And before starting the talk, I would like to feed a little bit your wanderlust with some images of my beautiful country. Chile has maybe not the best beer in the world, but that it's claimed by, for example, the Belgian researchers here, but it has really beautiful landscapes. The desertic landscapes, it has the Patagonia, which is really impressive, and the mystic of the Easter Island with these monuments that are known by everybody. I hope that you soon can visit us here in our country. What a best opportunity that we hope the next on-site IFORS conference that will be held in Santiago de Chile in 2023. Next IFORS conference will be in Korea, but it will be virtual. So that's a good opportunity for you to visit us. And also we organize together with Professor Richard Beba, also part of the NEEDS, the BAFI conferences, which are smaller conferences focused on business analytics, also machine learning. Some of you are here as well. And our last conference, which was unfortunately canceled, also included some of the NEEDS events. So there are many opportunities to visit us. So I highly recommend our country for you to pay us a visit. So I will try to squeeze the most of these 50 minutes I have. This is a 2-part presentation. The first part will be related with cost-sensitive learning. And the second part will be causal classification, ending with the combination of both areas. After a motivation for the 2 parts, I will present a novel method in profit-driven classification, and also a novel application, which is the mutual fund industry. And in causal classification, I will also present the third paper will be a novel application, student dropout, and also the foundation of this combination. That is the fourth paper I want to present. So I would like to start with a quote from probably the best known data scientist in the world, which is Nate Silver. And from his book, The Signal and the Noise, which is also probably the only bestseller in data science there is. Nate Silver became really famous for predicting the outcome of the Obama-McCain election perfectly. So he became really big and he wrote this book that became a bestseller. I was reading this book in bed one day. It's a really easy book to follow. And suddenly I kind of was shocked with this quote. Accuracy is the best policy for a forecaster. It is forecasting original sin to put politics, personal glory, or economic benefits before the truth in forecast. Sometimes it is done with good intentions, but it always makes your forecast worse. I was shocked because I am really, that's make me actually a sinner, because our research line is focused on putting economic benefits before accuracy, biasing the models towards the benefits and costs to make them our decision more profitable in business analytics. However, I believe it's okay to be sinners. We follow the research line created somehow by David Hunt, which said that statistical measures for model evaluation, such as accuracy, are not really adequate, and we should focus mainly on the primary goal of predictive task. So in medicine, for example, we will limit ourselves to binary classification. So that's basically translate in balancing the type 1 and type 2 errors and the cost of the benefits of the solution. Of course, in medicine, it's really hard to combine in one equation the cost of the mistakes, but we can do that in business analytics. And we can actually bias our model in order to make our decisions better, even if that causes that the models are not that accurate in terms of net accuracy. The main application is churn prediction here, and churn prediction is a part of this world, area of research in marketing, which is called customer relationship management, which is about creating long-lasting, profitable relationship with the customer. Decisions can be made basically from the gut, but also it can be done via machine learning and analytics models. And the three tasks that are important in this area are, I want to describe it here based on the customer life cycle of a customer. So we have time in the x-axis, the revenue on the y-axis, and the first task we can address with profit-driven analytics or causal learning is an efficient customer acquisition. How to avoid spamming everybody and contacting only the customer with a customized offer in order to convince them to enter the company. Or cross-selling, upselling, how to sell more to a given customer in the time of maturity. And finally, create longer lasting relationships, try to convince a customer in order to stay in the company when they are somehow demotivated and they want to leave. So that will be the main focus of the presentation. And customer retention is really important because engaged customers are more profitable than standard customers. And also it is said that it's more effective to perform retention effort that also money is well invested in retention effort because it reduces operational costs and also marketing costs. So let's put some number here. The benefits of retaining a customer is related with the customer lifetime value. if I manage to retain a customer, I will win the future revenues that I can achieve with the customer. Okay, so there is a formula for computing the benefit of a correctly retained customer. And there are also costs of the retention campaign. There are costs of contacting the customers, F, cost of the incentive that we will give them in order to retain them. And this framework developed by Verbeek et al. And Verbraeken et al. In 2012 is kind of the baseline case that we are considering in our study. So basically, instead of focusing on accuracy, we focus on the profit of a retention campaign. So if we apply a retention campaign to our customer base, we have two possible directions. So we can classify the customer as churners and apply to them the retention campaign. So eta is the fraction of contacted customers, or we can basically ignore them, and that leads to 4 different outcomes. There will be churners that are the correctly classified churners, the non-churners incorrectly classified, there will be churners incorrectly classified as non-churners, and the non-churners correctly classified. So the confusion matrix. If we target a will-be churner correctly classified, we can expect to retain this customer, but not always. Sometimes these customers are so fed up that they just wanted to leave anyway, and they basically ignore the incentive and they leave. That generates the cost of contacting the customers, and this happens with a probability 1 minus gamma. But with a probability gamma, they will accept the retention effort, they will be happy, and they will give me the customer lifetime value minus the cost of the campaign. This is the jackpot here. The customer lifetime value is usually much larger than the cost of the campaign. So here is what we want to focus on, the people that we can convince to stay in the customer base. Another possible outcome is the non-churners, incorrectly classified as churner. They will agree to stay in the company. They will accept happily the incentive, but they only bring cost. But because if I don't target them, they will remain in the company anyway. So that also brings costs. And here we consider that there are no monetary costs of with the customers that are not contacted. So this translates in a profit formula that balances the benefit of the cost of a campaign, which has this form, in which the model is considered here as the accumulated probability based on a decision variable, which is the threshold. And here are the other parameters of the model. And the framework suggests that we should maximize the profit based on the decision threshold. If we have a probabilistic model for binary classification, we should select the threshold such that it maximizes the profit. And that's also give us the optimal number, the optimal fraction of contacted customers. And the expected maximum profit criterion is very similar, but it considers the parameter gamma as a stochastic variable, which follows a distribution, in this case, a beta distributed random variable, and we compute the expectancy over gamma of the profit, and we maximize this measure. And this way we can identify which model is better, is suitable for our task. We can make the best logistic regression with the best threshold, but also compare among different classifiers like random forest, super vector machines, and select the best one, which is not the most accurate one, but the one that leads to largest profit. Okay, that was the first introduction. let's move to our first paper, which is profit maximization machine learning technique that we develop, and we developed that based on robust optimization. So maybe you recall the presentation of Bart Bessent in this line, in the different talks, that neat talks that we have a couple of weeks ago. This is kind of similar. We want to maximize the profit in the model training in order to make the learning machine to have the right objective at the beginning. And we discovered a model which was perfectly suited for that, and this model is from the robust optimization world. Robustness in machine learning is somehow a random fuzzy concept. It's not really clear, but we have been working a lot in how to convert robustness to different machine learning methods. Robustness is not the same of accuracy, but it means that the performance of the model does not deteriorate very much when slight changes in the distribution occur. This is important in business analytics because for example, in credit scoring, you have always evolving policies in terms of granting credit, or in churn prediction, you have also different campaigns. So the data is not really stable. So we want models that work relatively well, even with small changes in the distribution. And we developed this machine called profit-based minimax probability machine, in which the profit is maximized directly, and it has also very nice properties for optimization. Is a second-order programming approach which can be solved efficiently with methods such as quadratic interpolation. This is the method that we use, that we choose to adapt for profit classification. Is called minimum error minimax probability machine, which consists on these chance constraints. We have a linear hyperplane of the form W transpose X equals B, the bias, the intercept, the bias. And we want to classify that. We assume that the data, for example, the churners and the non-churners are random vectors that generate the samples with means and covariance matrix mu and sigma that are known from the data, and we want to classify correctly our churners or non-churners up to a rate eta 0 and eta 1, even for the worst data distribution for the given mean and covariance. And we want to maximize the performance, so the two class accuracies, the accuracy for the churners and the accuracy for the non-churners. And we can use a trick which is well known in the robust optimizations world, which is the Chebyshev-Cantel inequality, which casts this chance constraint problem into a deterministic problem with second-order comprogramming, second-order constraints, which are this one, and mu and sigma are computed from the data. So this is the original model from NPM, a deterministic second-order comprogramming model, but we thought that we can modify this. This theta that is somehow the weighted sum of the two class accuracies, we can adapt it using our profit metrics from the framework by Verbeke and Verbraeken. So we acknowledge terms. We replace the benefits and the cost using the formula of Verbeke. So we compute the profit as we cast this into a profit maximization problem in which we maximize the profit subject to this conic constraint that brings robustness to the model. And this is a nice linear model that doesn't have any tuning parameter. It's kind of comparable to the logistic regression, in which the profit is directly maximized. and that can be solved using quadratic interpolation. I won't go really into details here. We apply this to 9 different benchmark data sets for churn prediction using expected maximum profit as the main performance metrics. And we compare ourselves with some traditional classification models, with some robust optimization models in the literature, and also with some profit model classifiers. Profit logic was presented also but Bessel presented a couple of weeks ago. And the results were, let's say, relatively similar. No method clearly outperformed others. But if we establish a rank for the 9 data sets, we obtain that our proposal has the best rank, for the average for the 9 data sets, and for the 9 different classifiers was 2.55. So the model was, in average, the best. It was not able to outperform statistically some methods like MPM or the profit-driven methods, but it outperformed some others in terms of this metric expected maximum profit criterion. So we achieved really good predictive results, and also with very good training times. The methods were relatively fast in comparison to, not as fast as some of the fastest methods here, but relatively similar to other classifiers. And this implementation of the current implementation of the prof logic, prof tree, were based on evolutionary algorithms that were actually much lower than our proposal, which is kind of the state of the art. So we have here a nice model, theoretically grounded, that can maximize profit directly, has some really nice properties in terms of robustness, in terms of optimization, and lead also to the best average results. So let's move to the second paper, which is the application in the mutual fund industry. We started a project with a mutual fund company, and they wanted to implement a churn prediction model. And we find out that no one has really applied this into the mutual fund industry, which is, or investment in general. So that was our goal, to incorporate the profit-driven classification for churn prediction in this industry. And that is also the novelty. We have a really nice data set based on customer data, such as demographical data, the history with the company, but also in financial information, indicators, ratios of the performance of the mutual funds, and also the profile of the investors. But we don't only apply the model, we also propose a novel framework, because we found out an important problem in the framework of Verbraek and Verbeke, which is that they cannot really deal with, very well with a really heterogeneous customer lifetime value. This is the histogram, the distribution of the customer lifetime value, and you can see it's really skewed. Yeah, the customer lifetime value for this industry is computed as a commission charge as a percentage of the amount of money invested by a customer. And these investments are really heterogeneous. So what we decide to do is to create a multi-segment, multi-threshold approach, in which using one classification model, we're using one classification model, but we consider different segments and different thresholds for each one of the segments. And the segments were obtained using quantiles, but they can also be given beforehand by the company. So this is basically the idea. So we adapt the maximum profit criteria, the expected maximum profit criteria, but considering different thresholds. So this is the formula for the maximum segment profit criterion, which is the name of the novel metric we consider, which is basically an average for all the thresholds, for all the segments. So the segments are Q segments, and this is the profit formula we had before. But we have a tau, we have a threshold for each one of the segment. So now our decision variable is a vector, not a scalar value. And also we can consider the number of segments as a decision variable, or we can assume that as a parameter as well. That's also possible. And we maximize this profit, and that leads us to the optimal target, to optimal fraction of contacted customers. And the same with the expected maximum profit, we create this expected maximum segment profit criterion, which maximizes the expectancy for our stochastic variable gamma. We apply this to our data set from this company. There are we couldn't find any publicly available data set for churn prediction. So we have only one data set. We create two data sets, one for 1 month churn prediction. So we predict for the next month who will attrit, and for the next 3 months. Okay, so we have two data sets essentially. And we consider traditional classifiers, and we evaluate on different metrics, including our two proposals. And these two proposals are comparable to the traditional maximum profit criterion or expected maximum profit, because we are making the same assumption. The only thing that we are considering is more thresholds, more segments. And you can see the improvement here. Yeah, so we achieve an average of 20 times, more than 20 times in terms of profit by focusing, for example, in customers that has a larger customer lifetime value. Here in the second data set, the gain is not that extreme, but it's at least 2 times more than more profit in comparison with the other metrics. Yeah, so as an average for the different models. So how do we manage to win that much money in comparison with the others? Well, here for the 1 month churn, the models are not really that accurate, so they suggest that we should implement really small campaigns. But if we focus on customers with a large customer lifetime value, then we manage to make larger, also they suggest to make larger campaigns that consider more customers. The same with here with the 3 month churn is kind of similar. But this is not only a machine that for operational decisions that can help us with the that's just select customers. We can gain important insights by using the models in order, for example, to define the campaign. One parameter that was not clear at all for us, because we didn't have information of previous campaign, is the value of the incentive. So we did a sensitive analysis for the value of the incentive, so we can somehow see the range of the value in order to make profitable campaigns, and how to select and how to design the campaigns. So this is why it's really useful to have this kind of analysis for the model. Okay, let me just check on my time. Now we are moving to the second part of the talk, and we are focusing on causal classification. Causal classification, also similar to cost-sensitive classification, we move away from accuracy and how accurate the model is, and we focus on the effect of what we are doing, or the effect of what we are doing. In this case, the campaign. Yeah. Let's think, for example, of we have a churn prediction model, which is really accurate, but and we have a limited budget, so we can only select a small percentage of the customer for the campaign. The traditional approach will say, okay, focus on the ones that have the larger probability of churn, 0.9, 0.95. Focus on them. But as we saw before, these customers are probably fed up with the company and they want to churn anyway. They don't want a retention effort, they want to leave. So they can be considered as lost causes. They will not respond positively. If they are not target, they will leave. Yeah, but they will also not be amazed by the campaign, and they will respond negatively also with the campaign. So we are switching the focus in causal classification. We are switching the focus from the lost causes to the persuadables, which are the customers that are more likely to be convinced to stay in the company when targeted. So they respond positively to the target, but they respond negatively when they are not targeted. So, and probably these customers are close to 0.6, 0.7 probability of churn, and they are not really convinced to leave, but they will leave if we do nothing, but they won't leave if they are convinced. The other quadrants are the sure things, which are customers that they won't leave anyway. They won't leave if contacted. They won't leave if they are not contacted. So we just leave them and we don't need to spend money on them. And the do not disturbs, which are the customers that leave the company, that will stay in the company if I do nothing, but they respond negatively to the campaign here. So the campaign backfires and the customer want to leave. I always thought when I read about this, that this doesn't exist, that do not disturb is just for completeness, but no one will leave because of the campaign. Until I made this project in the mutual fund industry. The mutual fund industry is a good example that a campaign can backfire. Imagine, for example, you have investments and you receive an email like, we are in convoluted times, COVID times, your investment hasn't done really well in the last year, but you have to think this long term because these convoluted times will pass. If you receive something like this, well, some of you will take it as it is. You know that you have to think long term and you know that this convoluted time will pass. But some of you will get scared with such an email. You will remember, yes, I have investment and yes, I am losing a lot of money. I want to leave this company. So your campaign can backfire, and this is actually particularly true in the previous case. So the traditional approach in churn prediction is essentially ignoring the information of previous campaign, creating a training set and a holdout set, and computing a model trying to predict churn. In some other cases, you just focus on the treatment data with the campaign data. But the uplift approach is essentially computing kind of two models. One model with the treatment data, with the campaign data, with a control group, which is the customer that does not receive the campaign. And you try to evaluate a new customer or an existing customer based on these two models. And you try to maximize the difference between, let's say, the probability of retention given that you receive the treatment minus the probability of retention that you don't receive the treatment. If this difference is large, it means you can be convinced. There is an important effect of the treatment, effect of the campaign. If this difference is small, you are kind of lost cause or a sure thing, but you are not really affected by the campaign. If it's negative, you are at do not disturb, and you really should not focus on them. And this has been applied in several worlds. Response uplift, should we contact a customer or not? For example, customer acquisition is the more traditional approach, but also in churn prediction, contact targeting, which ad should I show to someone, channel selection, dynamic pricing, electoral politics. Yeah, you may remember Cambridge Analytica. Cambridge Analytica was a big fuss, not only because they presented false propaganda, not only because of the breach of information, but also because it worked. And it worked because they used these kind of causal models for selecting exactly the people they wanted to target, and they wanted to show this kind of false propaganda. Yeah, so this has been used previously in several applications, but we didn't find anything in this world for student dropout, which has been widely studied in the literature of machine learning and also in higher education. Is a very important problem, not only for private institutions which are based on tuition fees, but also it generates social cost. I mean, the government is willing to put money on to fund the students. So there is an important social cost of student attrition. Yeah. So we apply this in 3 bachelor programs for a Chilean study, for a Chilean university. We have we predict churn in the 2nd and 3rd semester, and we build covariates using information on the 1st semester. And the most important thing here is that we have retention efforts in the form of tutorials. It's not really a traditional problem, so we have to adapt a lot of things. The tutorials were designed to improve the performance of the students and also to generate more engagement with the university, but all students were invited, and there was a self-selection bias, which is also important. It generates some other issues. And the tutorials actually worked. So the churn rate for the treatment, the churn rate without the tutorials was 13%, 14%, and the churn rate was 12%. So the model actually worked, this open call actually worked, but what we wanted is to make, let's say, a customer call and customer tutorials in order to focus on the persuadables. That sounds really bad when we talk about lost causes or persuadables in student dropout, but we want to design a program that with a, let's say, a more mandatory call for the ones that we believe that the campaign, that the retention effort will make, they will have more value, instead of this open call for everybody that everybody can attend. We want to keep the open call, but maybe develop 2 groups, one customized and one for the open call. So as I said, the self-selection bias is a huge problem because there are important differences between the 2 groups in terms of the variables that we are considered. For example, the income is way different for low-income families usually take the tutorial, and in the other group they didn't take the tutorial. So what we do for balancing this, the traditional approach is propensity score matching, which is kind of an undersampling of the control group in order to balance these 2 measures, to balance the means. And the results we obtain, basically, we confirm that the traditional approach is really bad. I mean, we use random forest, independent of the accuracy. the traditional approach, if we separate in quartiles, so 25% of the students here with the largest probability of churning, if we focus on them, our uplift is actually negative. In contrast to the best uplift model we consider, which is a variant of gradient boosting, which achieve a way better approach in terms of uplift, in terms of selecting the ones that can be retained with this effort. We explore a wide variety of different uplift models, and this gradient boosting variation was the best one, the one that leads to the best results. Yeah? And if we focus in somehow the 25% of the target population, we can achieve way better results compared to a random selection. But again, this is not only an operative model for selecting students. This is also a tool for making better decisions. So we can understand the students that are more likely to be retained. And these are, for example, interesting chart, a radar chart that we can identify which students, what are the characteristics of the students that are more likely to be retained. Yeah, so this is important for the design of tailored tutorials for a percentage of the students. Okay, fourth paper. I have like 3 minutes, so this will go relatively fast. And this is not a new method, but it's basically a new line of research we are proposing here, combining cost-sensitive and causal classification. Yeah, so no method has before do this combination of the two worlds. So we develop a framework that integrates these different words: cost-sensitive learning, causal learning, and conventional classification, introducing the causal counterparts of the confusion matrix and the cost-benefit matrix. So this is the confusion matrix written in such a way that it is really compact, in a very compact way. So we have the confusion matrix for the predicting, let's say, churners or not churners. This is really general. The outcome class, the predictive class, and all the possible the type errors, etc. So, and this is the cost-benefit matrix in which we balance sensitivity, specificity, in the same way we did it with the cost-sensitive learning. So we can rewrite the profit metric as in this matricial form, which is really compact and really general, simply as the sum of the elements of the component-wise product of the two previous matrices. And we can maximize the profit, finding the threshold that maximizes this measure. And we proposed, in the same direction, a causal confusion matrix in which we have the outcome class and the treatment class. So you receive the campaign, you don't receive the campaign, you receive the campaign, and we can compute the proportion of the negative and positive outcomes based on the treatment and on the control group. And in the same direction, we can make our causal cost-benefit matrix, which is also the benefits and the cost in the control and the treatment group. And it is the same operation for computing the causal profit. Yeah, the causal profit, in which we also have a causal threshold, which can be maximized, and that which leads to the maximum profit of a causal problem. And this is written in a really nice compact way. We can simply replace some of the values. For example, for churn prediction, the causal cost-benefit matrix for churn prediction is the one that I described at the beginning, with the customer lifetime value for the one in some cases, and the cost of contacting, the cost of contacting the customer, and the cost of the incentive. And this way we can merge the two worlds, and we believe it's a really interesting way, a very interesting line of research that we can consider. So to finalize this talk, these are the 4 papers I talked about. The first 3 are already published in journals such as European Journal of Operational Research, Omega, and Decision Support System. The last paper is submitted to European Journal of Operational Research, but it's also available in archive. So thank you very much. I think I am on time, 45 minutes. So I will leave the space for questions.
Thank you very much, Sebastian, for this very interesting presentation and very based on lots of papers that you are working on. So as we usually do, we open the floor for questions. And ideally, yeah, you can unmute and show your video, yeah, if you have questions. We don't have raise the hand button. Well, we do actually, yeah. So who would like to ask a question to Sebastian?
I got a question, Dolores.
Yes, Luis, go ahead, please.
Thank you, Sebastian, for your wonderful presentation. I have a question about the first topic you talk about. When you talk about this robust optimization, when you create some constraint for the optimization, I'm thinking about another way to solve that, because that it's an stochastic optimization, right? The objective function was stochastic, and you try to avoid that the performance in the test set wouldn't be so different or bad as the training set. I'm wondering if you can apply something like penalization of some sort of C-bar or some kind of instead of modifying or adding constraints to modify the objective function in terms of C-bar, or penalizing some kind of fluctuation in the test data set. I don't know if you what I mean in terms of the stochastic optimization.
Yeah, thank you, Lucho. I think, well, the final model is deterministic in the sense that we make some assumption and we cast the chance constraint. Actually, we have probabilistic constraint. The objective function, we are not assuming. Maybe it is confusing because we are considering, for example, eta, gamma, which is somehow an stochastic parameter, which is the probability of accepting an offer. But here in this case, it's just it's a deterministic model in which the objective function is it's a linear function, deterministic, and also the constraints are deterministic when we use this traditional trick for robust optimization, which is the Chebyshev-Cantel inequality. Of course, what you are suggesting is another way to go. I believe and we have been discussing some ideas on how to make the model robust, how to incorporate uncertainty and risk in the decisions, and how we can make better decisions taking into account, for example, standard deviations. I believe it's an interesting model. I think we can adjust this one or other models in order to confer robustness to different models, in which, of course, in the financial world, C-bar are an important concept. And for example, in machine learning, we don't we don't consider this robustness because it's not a traditional problem, but in the financial world it is. So I believe it's an open problem, how we can confer robustness to the models, and maybe we can take some good practices from the financial world and incorporate in the machine learning world. I think it's a very interesting suggestion.
Thank you, Luis, for your question. Is there any other question from?
I also have a question.
Okay, go ahead, Marcela.
Hi, Sebastian. Thank you very much for your presentation. It's very interesting, the part about student dropout. I am currently working on something with data from Colombia. I'm originally from Colombia, and I'm using some prediction models to predict a school dropout, but it's for high school. And I wanted to, can you comment a little bit about this in the results part? In the last part, you talked about relevance of predictors. And I didn't understand if that was after you did this causal classification, or where does this come from?
I assume you mean this slide?
Yes, yes.
Okay, great. Well, thank you for your question, Marcela, right? Marcela.
Yes.
So, yeah, I mean, the causal model, the output of the causal model is kind of a rank of students in terms of their uplift. So ETE in the causal inference world. So in terms of, so the first quartile are the 25% of the students with a larger ITE or a larger uplift, meaning that they are the ones that have a larger difference between the probability of retention with the treatment and without the treatment. So we can compute the values. I mean, we can compute the averages of for this. Imagine we are separating the whole data set into 4, and then we can compute the average for the various attributes for each quartile. So these are the characteristics of, for example, in blue, the difference are relatively are not that strong, but in some cases we observe that for example, we should target, for example, customers that are, and here also we have normalized variables that are binary variables. For example, this is a binary variable. It belongs to a private school or not. So here are the students that are more likely to be convinced by the tutorial are in average from public schools. They have some good performance in some classes, but some relatively poor scores in mathematics, for example, in the PSU, which is the SAT equivalent. So this is the entrance test for the university. So we can somehow characterize the students, and this can somehow help us to create, to design better campaigns and to understand which are the variables that are more important. I mean, the future selection, as I mentioned, Dolores, is one of my, I did my PhD on future selection, and I think the most valuable insight of future selection is not the performance, but also the interpretation that it provides. It gives me the intuition of which variables are characterizing the different segments, and with this we can use better decisions. I don't know if that answers your question.
Yes, yes.
Okay.
And this is after you did the matching to account for this selection bias, right?
I think this is the test set. The matching was, of course, the matching is biasing the model only for training, and then I did, this is kind of for the test set.
Okay.
Yeah. So which is
so the model is trained in with after the matching with
yes. The matching is kind of it's the same as a solution for the class imbalance problem. You want to train, you want to adjust your training in order to make a better model, an unbiased model, but then you apply it on a test set that is not corrected for class imbalance. Yeah. So because then it will be totally, of course. After this is the test set and it's not corrected.
Okay, great. Thank you very much.
Okay.
Thank you very much, Marcela. Is there any other question in the audience? Yeah, I was like Marcela, very enthusiastic about this model last paper that you have presented. You have there some parameters in the confusion matrix. So these parameters are they given to you, or if they are not given to you, how do you choose them? Do you do sensitivity analysis on them?
You mean for this particular case or for the last paper with the causal cost sensitivity?
Yeah. For the last paper, sorry. Yeah.
Okay. This is a general framework, of course. This is, I mean, for example, if we
over here.
If we model churn prediction, then we will have a lot of parameters which are the cost and benefits of a retention campaign. For example, for the problem of the mutual churn industry, there were some parameters that we have basically no idea. We have to make some guesses, and we did some sensitivity analysis, like the incentive. Yeah, the cost of the incentive is something that we just didn't know how to do it. So this gives us a range in which our model is profitable and how to select these parameters. Some of them, for the first papers, we use, let's say, the standard parameters for churn prediction provided by the literature. And for this paper in particular, for the cost-sensitive causal learning, well, this is kind of a general framework. You should put your own inputs here, and then you will be able to compute the cost, the causal cost benefit profit of your solution. Okay.
Thank you so much. I found it very interesting. Is there any other question from the audience? Well, if not, we would like to thank you very much for opening to us new venues in machine learning and getting, closer to what you would do in econometrics and other fields in which this causal is very important. So it has been very inspiring, and thank you again for coming to the
Thank
online
you, Lolia,
seminar.
for the invitation.
Thank you very much. And well, to the audience, thank you very much for coming today again, and we see you next week at 4:30.